Hello everyone, my name is Taemin Park and I'm a PhD student at UC Irvine. Today I'm going to talk about NoJITsu, locking down JavaScript engines. This is a joint work of UC Irvine and KU Leuven. Today we cannot live without internet, so web browsers are now essential parts of our daily lives. Many of you might open a web browser first as soon as your computers are on. One of the biggest innovations in web browser is JavaScript, which provides rich interaction between web pages and web browser, so people can enjoy the dynamic web environment. As you can see, most of the modern web browsers have JavaScript engines embedded. However, the problem of the JavaScript engines is that they are usually written in unsafe languages such as C or C++, so they might contain vulnerabilities. Also, JavaScript engine automatically runs any script embedded in a web page. Therefore, it is easy for an attacker to inject his script and trigger the vulnerability to exploit victim's machine. JavaScript engines continue to evolve and the size becomes larger and larger. As you can see in this graph, the code lines of V8 now become more than a million. Accordingly, every year, more than hundreds of vulnerabilities in JavaScript engines are reported. So JavaScript exploitation is now a real threat. One of the famous JavaScript engine exploitation is JIT-spraying attack. In this attack, an attacker encodes malicious code in the huge number of constants in script. Look at this example. They are definitely benign consecutive XOR operations. So there is no problem in generating corresponding JIT code within the sandbox. However, an attacker can trigger a vulnerability and change the program counter to the middle of those constants. Then the semantic of the code turns into what attacker wants to execute. In this way, an attacker can inject any malicious code within the sandbox. There are more advanced attacks on JavaScript engines, especially utilizing multi-thread capability. Look at this slide. During the JIT compilation, JIT compilers first generate the intermediate representation, which is JIT-IR. At that time, an attacker spawns a new thread and steals a CPU cycle to overwrite JIT-IR. Then the JIT code transformed from the corrupted JIT-IR eventually contains attacker's code. Or by using the similar technique, an attacker can inject his code directly onto the JIT region when it becomes writable. So people suggested several defenses, mostly isolating JIT components through separate process or trusted execution environment. However, the basic execution unit of the JavaScript engine is the interpreter, but previous work is all about JIT, and there have been no attacks and, of course, no defenses on the interpreter. So here's our contribution. Our first goal is to discover a new attack vector, which is bytecode interpret attack. Our attack corrupts the bytecode interpreter and escape from the sandbox, so that an attacker can execute arbitrary system codes. The second goal is propose defense mechanisms to protect JavaScript engines. Our defense techniques pursue a comprehensive defense so that it defeats not only the bytecode interpret attack, but also prior JIT code injection and code reuse attacks, which means protecting entire script engines. Before going to talk about our attacks and defenses, I will go over how interpreter executes. Look at this slide. When script is about to be executed, it is compiled by bytecode compiler, which generates bytecode object tables and JavaScript object. Bytecode is a stream of the bytecode instructions, which are executed by the interpreter one by one. Bytecode instructions are pretty much similar with machine instructions in that it has opcode and operand. However, instead of specifying data directly on the operand, it is used to specify an index of an object table and each entry of the object table points to JavaScript object where actual data are stored. Here, our attack aims to utilize the function call routine to run arbitrary system calls. We have several attack strategies, but in this talk, I will show one attack example which corrupts JavaScript object. Here's our threat model. There's at least one memory corruption vulnerability inside of the script engine that gives an attacker an arbitrary read and write capability. And we assume that code injection defense is deployed, so memory region should be either writable or executable. Lastly, our threat model has lightweight code reuse defense, which includes ASLR and coarse-grained CFI. This is a simple attack script calling a benign function foo, and the function foo calls cosine function. When this script is compiled, corresponding bytecode, object table, and data objects are generated. Here, calling the cosine function is achieved by an indirect function call where the function pointer is fetched from the load function bytecode instructions, and also arguments are fetched in the same way. And this indirect function call gets the address of the context object as the first argument. Here, we're gonna add code to trigger a vulnerability, which gives an attacker an arbitrary read and write capability. So attacker can now rely on arbitrarily read capability to find data to corrupt. Here, let's say bytecode, var1 object, and context object. We use a heap layout inference technique, which first leaks an address of an arbitrary object and follow the pointers in the object to find other objects. We repeat this process recursively until we get to the target data. After finding them, the attacker utilized the arbitrary write capability to corrupt them. First, it corrupts the bytecodes so that the operand of the load function instruction points to var1 object. Then it corrupts the var1 object, so it contains the address of the system function. Finally, it corrupts the context object so that it contains a share command. So when this script calls the function foo, it will execute the system function with the share command. So in order to protect the script engines from the previous bytecode interpret attack, we propose NoJITsu, a new defense mechanism. The goal of the NoJITsu is protect all the data that are targets of our bytecode interpret attack and other existing attacks. So we consider bytecode object tables, JavaScript object, JIT-IR, and JIT code. In order to do this, we enforce a fine-grained memory access control over all those data, which means we try to minimize the permission of each data as small as possible. However, of course, memory permission controls inevitably comes with significant overhead. So we decided to use Intel Memory Protection Kit to solve this problem. Intel MPK is a new hardware feature to control the protection of the memory chunk in an efficient way. It doesn't need to change the permission bit in page tables, so it's very fast. Look at this slide. Each memory chunk is assigned up to 15 kinds of specific MPK keys with associated permission. Changing permission is achieved by simply changing a permission bit of the specific key at PKRU register, and then every chunk with the specific key is affected. Also, MPK supports execute-only memory, which mProtect does not support. Finally, MPK is thread local, so every thread has a different view of memory permission of the same chunk of the memory. We are going to apply those nice properties of the MPK to memory protection policy in the script engines. This is the legacy policy where bytecode object tables, JavaScript object, and JIT IR are all time writable, which means they are always open to be corrupted. JIT code is readable and executable, which allows the attacker to learn about RP gadgets for attacks such as JIT. JIT code becomes temporarily writable when it is embedded to the memory, and like we discussed earlier, an attacker can inject his code by utilizing race condition. So in our NoJITsu, we minimize memory permission as small as possible. Now, bytecode object table, JavaScript object, and JIT IR are all-time readable, and JIT code is execute only. On top of that, we separate the memory chunks into different kinds and assign different MPK keys to manage them individually. For example, when there is an instruction to write on object tables, we only open a write window of object table for this instruction so that other kinds of data are not affected. Moreover, attacker no longer utilizes race condition because the write window is independent from attacker's thread. But there are challenges we need to solve here. It is required to open write windows for all legal write instructions to those data, and finding all of them is challenging, and implementing protection changes is also not trivial. Then let's start by the easiest one. We found that bytecode object table, JIT IR, and JIT code need to be writable only during the compilation. So we manually find the right instructions to those data and implement protection changes before and after the instructions. However, we found that it is not trivial to make the JIT code execute only because JIT code is a mixture of machine instructions and readable data such as jump tables and large constants. So we separate the JIT code into machine instruction part and data part and assign different MPK keys to them. So now we can make the machine instruction execute only and data section read only. Now we get to the most difficult one, JavaScript object. There are so many JavaScript objects and also so many write instructions to them. So it's impossible to find them and instrument our protection changes manually. Therefore, we need an automatic solution to find those instructions so that it can be generally applied to any JavaScript engines. We can rely on static analysis such as point-to analysis, but they are found to be conservative, so it is not suitable for our fine-grained enforcement. That's why we decided to rely on dynamic analysis. The goal of our dynamic analysis is to automatically find all the locations of write instructions involved in JavaScript object. So we instrument the code for every write instructions using LLVM and check this properly. After the instrumentation, we run script engines with well-chosen input set while making JavaScript object read only with an MPK key. When a write instruction tries to write on an object, it will cause segmentation fault because it's read only. Then our custom signal handler checks whether it's because of the MPK violation. If it is, it changes the permission of the object as writable and return to our instrumented code. Our instrumented code then checks whether the permission becomes writable, which indicates that the write instruction above touches the JavaScript object. Then it reports the associated location and makes the data object read only for the rest of the analysis. After finding all those locations from our dynamic analysis, we use LLVM again to enforce permission changes at the start and at the end of the function so that we open a write window for the entire function. We also did a little bit optimization for some cases where an instrumented function is called in a loop. In this case, we hoist the protection changes out of the loop. In this way, our dynamic analysis automatically finds and instruments all the right instructions. In order to find all of the functions involved in JavaScript object, it is best if our input set guarantees full coverage, but it's impossible. So we studied script engine and found that those functions have commonalities, and we can categorize them into 4 accessor functions. Those accessor functions work as gateways to write on data object and extensively shared by other components. Therefore, we only need to find those accessor functions, and we believe that the extensive test cases on every kind of data object will cover them. That's why we decided to use JavaScript test suite, which satisfy our requirement, and we're going to show that our assumption is correct in our coverage analysis. In our coverage analysis, we picked one fixed for test suite as our input set for dynamic analysis and implemented NoJITsu. Then we ran this NoJITsu-enabled JavaScript engine with a full test suite, and we found that all the test cases are passed without any errors. So our analysis implies that even a small set of the test suites is enough to find all accessor functions. We also evaluate whether our defense can defeat our bytecode interpreter attack, code injection attack, and other kinds of code reuse attacks. In our bytecode interpreter attacks, we need to corrupt one of the data among bytecode object tables and JavaScript object. However, NoJITsu makes them all read-only, so attacker cannot manipulate them anymore. JIT code injection attacks are also not available. JIT IR and JIT code should be writable for the JIT compilation unit, but it's not for attacker's thread, where JIT IR is read-only and JIT code is execute-only. This is because of the independent view of the thread for the protection of each memory chunk. So attacker cannot overwrite it anymore. Our defense is also effective in advanced code reuse attacks such as JROP. JROP basically tries to harvest RP guts at runtime by traversing code pages. But after enforcing NoJITsu, reading code pages are not available, which disallows harvesting RP gadgets. NoJITsu can be combined with constant blinding to effectively defeat JIT spraying attacks. Constant blinding is a good technique to defend against JIT spraying attacks with large constant, but not effective with small constant because of the overhead. In order to exploit the small constant, JIT spraying attack should be combined with RP style attacks, but our NoJITsu invalidated because NoJITsu does not allow harvesting RP gadgets, which is already described in previous slide. This is the performance evaluation of NoJITsu. We tested our NoJITsu on SpiderMonkey, which is one of the famous JavaScript engines. And we used long spider benchmarks, which are a longer version of the standard benchmarks available in WebKit. The reason that we use those benchmarks is that the original benchmarks are too microscopic to catch the overhead caused by our enforcement. We ran those benchmarks on Intel 0 machine under Ubuntu 84.1. Here's the result. The x-axis is benchmarks and y-axis is overhead induced. And the blue bar is our NoJITsu without optimization, and orange bar is NoJITsu with hoist optimization. As you can see, the average overhead of our defense is 5%, but it is reduced to 3% with our hoist optimization. Our hoist optimization actually widens right window, but it's negligible. You can check more details about this issue in our paper. Okay, I have to conclude my talk. We showed an instance of bytecode interpreter attack, which corrupts interpreter execution to run arbitrary shell commands. So we proposed NoJITsu, enforcing fine-grained memory access control through intent MPK. And we show that our defense successfully stopped code reuse and code injection attack, and also the bytecode interpreter attack we developed without incurring much overhead. And this is the end of my talk. Thank you for your attention, and I'm happy to answer any questions.
Okay, is this the question section now? Yeah, I think my browser is really slow, so now I can see, yes, some questions. Okay, yeah, okay, yeah, let's see. Yeah, I can see the first question is the eval percent overhead. What was the measuring again? Yeah, this x-axis is the benchmark itself, and the y-axis is the overhead, which means that we have kind of a baseline, which is the running JavaScript without our protection, and then we run the JavaScript with our protection, and the overhead ahead is how many percentages increase from baseline to our protection version. Also, the second one is the question is, I think you touched based on this already, but did you say traditional SAST testing is not as effective for this? Can you clarify more some details about this question? So I couldn't understand that. So you mean the SAST is a static analysis? If it's correct, and then yeah, as I told in the talk earlier, the static analysis is kind of conservative, so it's fine. It can, there's no false positive, but the static analysis also consider the huge number of objects there that don't need to be protected. So that means we are going to widen the attack windows. So attacker has more high probability to write on that object, because that object, most of the objects are becomes writable most of the time. It's going to be more than 50% of the time of the execution, I think. So down millisecond, just percentage. How many percentage increase from baseline to protected version? I think I already answered this question. And also I think I already answered the question about why the static analysis is not good for my work. So we can just do some kind of the value set analysis, which is that we can just imagine how the memory structures looks like for each code section, and then we conservatively say this memory section should be protected because it might contain our core data, but it might not contain our core data, and there are so many cases that cover this kind of situation. So it is not that fine-grained. Baseline, kind of, both are kind of nanosecond, millisecond. I don't remember. Something like that. Around nanosecond. I think. I'm sorry that my browser is really slow, so I can see the question very late. So I thought that there's almost no questions at all. So, yeah. So, and in addition, so I use the benchmark, which is the long spider, that is the longer than the standard benchmark. And this, actually the standard benchmark, each benchmark finishes within around 1 second. Sometimes, no, around some millisecond, but longer spider is around 100 times more, yeah, more than that. And but there's no difference in what kind of things are tested. So yeah. NoJITsu is not browser plugin. In my talk, I already told you that I just modify and instrument and update the JavaScript engine codes by just manually just engineering JavaScript engine or using element instrumentation tools to automatically insert some necessary codes in it. So if someone wants to use NoJITsu, they have to build the JavaScript engine with the element instrumentation paths that I made, and also they have to have the NoJITsu version of NoJITsu enabled JavaScript engine that I implemented. So I also think that after polishing my code, I would publish the NoJITsu enabled JavaScript engine to the public. Okay. So I think until now I answered most of the question, and there's some time that I can talk with some missing point. And actually, the dynamic analysis doesn't catch every cases. There are kind of two corner cases, and one is for the garbage collection, and the other is for kind of generating multiple copies of the function. In the garbage collection cases, dynamic analysis cannot catch because the behavior of the garbage collection is kind of random. So what I did is that we just look at the code section for garbage collection, and if the garbage collection tries to write some object value, we just conservatively to open the right windows for them. And also, compilers sometimes generate a multiple function for one specific function, especially when they have some kind of template argument, and then so our dynamic analysis will just catch some of them, but not all of them. So we just find these cases and instrument our protection changes for all copies of those functions. And thank you for the comments. I really appreciate it. You guys like my work. So also, what should I tell you? There's something that I need to clarify. Oh, also, we just assign the key to specific data domain, but we separate the object into two kinds. The one kind is just primitive object. The other kind is kind of the crucial object. The reason is that attacker just try to exploit some, or usually they exploit some kind of buffer to override really critical data. So object which contains the array should be separate from the object which contains the critical data. So we separate the object into two domains. And actually the NPK provides 16 domains, and we only use six domains. So if we want to make our defense more fine-grained, we can just separate the other data also. So there's a possible way there are a lot of possible ways to improve the security of the current version of the NoJITsu. Okay, so I'm looking at questions. Yeah, we can do that. Yeah. Yeah. Okay. Yeah. Cool. So I think there's no question anymore. So yeah, thank you for just attending my talk, and I really appreciate it and enjoy this Black Hat talks. Thanks.